So the next scheme for this numerical integration is the trapezoidal rule. So the idea was, of course, for the midpoint rule that, well, we know how to compute the area of a rectangle. It's easy. But, you know, we also can easily compute the area of a trapezoid. So maybe it would be good, instead of making those guys rectangles, to make them trapezoids. So here is an example of what a trapezoidal rule or a trapezoidal approximation would look for our example here. So let me like this. It's not really like, it doesn't look that good with 8, right? Because you've got this big undershoot at the bottom, but we can make it better. So you see, once we get up higher, it is better, right? And you're gonna get this kind of nice there. So we'll see. I'll show you then how to set up how we would do this problem. Okay. So what we're doing then for these trapezoids is we're taking our partition, and what we're doing is we're making a trapezoid based on those 2 points, the xi minus 1 point and the xi point. So we're taking the line between the 2 endpoints of the interval. Okay. So let's see how that works though, right? So what is the area of a trapezoid, right? So if I have just like some regular old trapezoid here, the area, it's going to be the height times the average of these two, right? So area is height times width 1 plus width 2 over 2. Okay. Now for our problem, right, our trapezoid is going to look something like this. The height is just this delta x, right? And these widths are going to be f of xi minus 1 and f of xi. So in our case here, each trapezoid area is going to be delta x times f of xi minus 1 plus f of xi over 2. Okay? So you can see that you're going to have this thing. Now we don't need to worry about calculating the midpoints. So that's kind of nice because we're just going to use the endpoints of our interval. And then what are we going to do? We are going to add all of these up, right? So I equals 1 to n, and then this is going to be Tn. Okay, but let's look at what this is, right? If I really write this out, I have delta x over 2 because delta x is the same. Now, if I start from I equals 1, I've got f of x0 plus f of x1, right? And then the next step is going to be f of x1 plus f of x2. So if I write all of these out and I keep going, all the way to f of xn minus 1 plus f of xn. But if I look at this, you see what happened with f of x1, there's 2 of them. Because from the first interval and the second interval, they both have that point. On one, it's the right endpoint. On the other, it's the left endpoint. And that's going to happen for f of x2 as well, because the next one here will be f of x2 plus f of x3. And then it'll keep on going. So all of the middle ones will have 2 of them. Only the endpoints at the very end will have only 1. So I can rewrite this. I'm going to rewrite it up here in the form Tn is delta x over 2, and then we've got f of x0 plus 2 f of x1 plus all the way to 2 f of xn minus 1, and then the last one, f of xn, is just by itself. So I can do exactly the same thing to figure out this problem again, because I already did the partition, so I'm going to use it the same. I'm going to use n equals 8. And what you see now is if I do this, I'm going to have 1/2 times my pi over 8. And now f of x0, well, it turns out that we're starting from 0. So f of x0 is going to be 0, right? Because I've got sine of 0. And then I've got 2 sine of pi over 8 squared and 2 sine of pi over 4 squared, all the way to sine of the last one would be 7 pi over 8 squared. And then finally, sine of pi squared is my last point. Mind you, it's not sine of pi, so it's actually not 0. Sine of 0 is 0, but it's a sine of pi squared, so it's some other thing. So, and then when I actually add all this stuff up, I get 0.696903. Okay? So these two are pretty off, right? Because for my midpoint one, I got like 0.8, and this one I got, well, 0.7. So it's going to be somewhere, the actual answer is going to be somewhere in the middle, but 8, in this particular case, you saw from the picture that in both cases, there was a significant overshoot, undershoot going on with both of these rules for n equals 8. N equals 8 is not enough to get you a really strong result. We know it's like somewhere in the neighborhood of 0.7. Okay. Oh, and by the way, let me talk about that really quickly just to get you the idea. So why do we have these different rules? And we're going to learn another one in the next video called Simpson's rule. So those 3 are the ones that we're going to be using. So why do we have other rules? Well, you see, before we had a computer that could just spit the answer out to you, some poor schlep had to sit down and calculate this, right? So the more endpoints you had, the more calculation was required. So they came up with different ways of doing it so you could get a better result, a closer result with less endpoints, right? So n equals 8 endpoints. The work is going to be in actually calculating this stuff. If we can come up with a better way of getting a faster result with the same number of endpoints, that makes a lot of sense when you're actually doing it yourself and you can't just take a little scroll bar and put n up to 50.